Okay, let's give this a try here. I'm going to review 2.3 concept of force, and just going to go through it. I went through this rather quickly the other day, or not rather quickly, but still, went over the basics. So, big things about force is we're going to start introduce that fundamental unit mass, which is measured in kilograms, and then we're going to talk about gravitational field strength, which is that little g, which ends up being in units, ends up being newtons per kilogram. So at the surface of the Earth, basically what you end up finding is that the field strength is 9.8 newtons per kilogram, or negative 9.8 newtons per kilogram. So that means if you have a kilogram and you hang it from a scale, you would end up finding that it has a weight of 9.8 newtons. So if you take this concept of G and M, and you multiply them together, then you end up getting the weight of an object, which is a vector. So here we have this is a vector, which is negative downward, and this is a vector, and then mass is a scalar. So real quick review of weight, and then there's just some different types of forces. Remember, force is pull or push on an object, and so that's what the main part of this chapter was about. So we wanted to draw vectors to represent these forces. So some other forces that we mentioned in class were tension, which is, you can find that in string or a rope, or that says string. Doesn't look like it. And then we also have a normal force, which is basically, for instance, if you had a book on a table, then the normal force would be the force of the table pushing back up on it. It basically means the force perpendicular to the plane. So if you were to, we know that we have gravity pulling this down, so you have to do that with a nice vector, and we call that W for weight, or you could also call it mg, since W equals mg. And then we also have the normal force normal, pushing back up. And so if we incline the table just a little bit for some weird reason, we just wanted to make mom and dad mad and make all the plates fall off, we would now have the normal force going like this, force normal, and then mg would still continue to be straight down as follows. So the other forces, that normal force, tension, drag force, sort of, I don't know. It's for instance, if you drop that coffee filter downward, there's my nice looking coffee filter, little ruffles along the edge there to catch the basket of, there's the coffee in it. No, we don't want any coffee in it right now. Strike that. Okay, there. And so it's going to be pulled down, and of course it encounters air pushing back up on it, and that is the drag force. Swimming, you could also talk about swimming. Swimmers encounter a drag force. Anything moving through air encounters a drag force. And then I also mentioned the force buoyant, FB, which is the BOUYANT, which is a force from the water pushing back up on a floating object, or even a submersed object, because as you probably know, you weigh less in water. The reason you weigh less in water is because when you're in the water is pushing back up on you more so than the air. So you end up having, and if that force buoyant is actually greater than your weight, then you would of course float. So moving onward, friction is the main one that we're going to probably focus on in here. Well, not probably, but will. And if this is just a simple force, that let's just say I have a block that I'm pulling, there's my force applied, we'll call that force applied, that's me pulling it, and here's an interaction right down here, and let me see if I can highlight that for you. There you go. That little interaction right there that takes place in the interface between that box and the table creates a frictional force, and that friction force is of course going to go back this way, and it's going to oppose the motion of the object. So even if I were to remove my hand and push it and let the box slide along the table, well, there would be no, think about that, what I just said. I pushed it, and now it's sliding by itself on the table. There is no more force applied because my hand's not touching it anymore. but it still would have friction acting on it. It would be the only force acting on it at that point in the horizontal direction. You would still, of course, have let's go ahead and bring this all out, the weight of the object, and you'd have the force normal of the acting on the object. So this is getting to a concept. I can just sort of go ahead and use this this right here to talk about a free body diagram. And free body diagrams are just where a concept where you remove all the box and the table and everything else, and you just make a very simple dot that represents, in essence, the center of mass of the actual object that you want to talk about the forces acting on. So let's take this object that's on the same page, this box sliding over, and let's draw all the forces acting on that object. So it sort of makes it easier for you to see, is what I'm saying. So we have force applied, we have weight, or mg. I'll continue to do that for a while. You can choose whichever you want. I like mg. The reason I like mg is because it tells me if I'm given the mass of the object, then all I have to do is plug it in, since I know g, and now I know the weight of the object. Or if I'm given the mass of the object, if I'm given the weight of the object, I can always get the mass of the object because I know g. So you get what I'm talking about. And then we have the force normal, and then we have the force of friction. So here, not according to a scale or anything like that. We don't know what the scale is. I'm just trying to give you a point here. This is a typical example of a free body diagram. Let's just click the page and go and look at maybe another one. How about a kid on a swing? A kid on a swing. So here's the kid on the swing. They're out here. There's the swing. There's their legs hanging off. They're a master of learning how to pump the swing and make it go faster and faster. And they're doing it with no hand. No, they're holding on. There we go. They're holding on, and they're swinging back and forth about this fixed point right up here. So let's just take them from that point of view right there. What would that kid look like? Besides happy, he would also have a free body diagram acting on him. And so let's take a look. Well, what do you know is acting on this kid? Well, that's a string. Well, hopefully it's a rope. Anyway, that's tension, force, tension. And then what's the other force? Well, it would be mg. So, which again equals W. So there's an example of a free body diagram of a child on a swing. At the very bottom, let's just sort of take them from a point of view of the very bottom. So the dashed line right there, it means that the kid is now at the very bottom of the swing. So how would it look now? So this relates to that diagram, and then here's the kid down here, with a dotted line. Just imagine that. So here I'm going to down this way. I'm going to put this diagram. So now you can imagine it would be force tension here and mg there. All right, going onward. So that's the basics of that one. So now we're going to get to 2.4. I'm 8 minutes into this. 2.4, that's Newton's first law. If you recall Newton's first law, pretty simple. Big key word is inertia. And inertia is a classic is resistance to change. Now, write down this other stuff that I'm going to say because I'm not going to write it down, okay? Basically, it says if you have an object, a body, and it's moving, then it will continue to move unless it is acted upon by an outside force. And so it'll continue to move in that straight line until an outside force comes along and acts on it and causes it to change its direction or change its speed. You get the idea. Now, what about internal forces? So let's just quickly, I said external force. If you had internal forces within the car, for instance, if you pushed on the back of a seat of a car rolling along down a road, that's an internal force, and you're not going to change the direction of the car, nor are you going to slow it down, so it won't save you. So inertia is the big key here. Resistance to change. Bodies do not like to change. The only thing that will change them is an external force acting on them. So then we just start talking about equilibrium. What does it mean to be in equilibrium? So you can have unstable A-B-L-E, or stable. And those are just simple little terms that you can read quite quickly in the book. But both of these are, let's point them this way, EQ, and that way. That's an arrow pointing that way. Right? U-I-L-I-B-R-I-U-M, equilibrium. Unstable just means, would be, here's an example of that only I can do. I can balance a ball on top of a pyramid. That ball, if it was in equilibrium, it would be very unstable, and any little bump would cause it to become unstable. Stable would be a book on a table, for instance. Nice and stable. Even a little bump on it is not going to cause it to get out of equilibrium. So, but the key about equilibrium, E-Q-U-I-L-I-R-I-U-M, right, is that the sum, that's the sum, that means sum, sigma, of all forces is equal to 0. So when you add up all the forces, so if you go back a couple pages and you look at the table sitting on the tabletop, then the sum of all the forces acting on it add up to 0. So mg downward minus force normal upward equals 0. If I happen to pull on it and my applied force was equal and opposite to my frictional force, then it would still equal 0. Just because the sum of the forces equals 0 does not mean that it's not moving. It could be moving along at a constant velocity. But it does mean that it is not accelerating. So key thing here is that if the sum of forces equals 0, then it's not accelerating. There we go. Accelerating. But so that just because it's not accelerating, remember we've talked many times about constant velocity, so it could either be at rest or constant velocity. And I'm at about 12 minutes. I'm going to run a little bit over. Let's try to. Oh, well, never mind. I'll get done when I'm done. Okay. So when you look at equilibrium, this is 2.3. So let's just take a case in point. Let's just say a street light. A street light hangs across a street, right? That's hence the street light, and there it is right there, sort of squashy looking. But there's red, green, and yellow, and it's hanging across. And I accentuated the angles here. But think about this for a second. So what would if you were to add up all the forces in this, and notice I'm identifying that dot right there because I want to focus on that dot. If you add up all the forces in this, guess what they would equal? They would equal 0. So that makes it pretty nice. That allows us to calculate the forces of this object. So that are acting on this object. So let's take a look. That's tension. Let's just say it's rope or cable. It doesn't matter. But let's call that T2 since I'm going to work left to right. And then this is T1, then this is mg. Pulling, well, no, I'm sorry. That actually is T3. There we go. And then T3 would be equal and opposite to mg. But we'll talk about that here in later. But so therefore T3 basically equals T3, if you want to talk about it, actually equals mg of the street light, which would be pretty heavy. Have you ever seen those things? They're huge. They're like 4 feet tall. I wouldn't want one to fall in my car. So here's what I'm going to do. I'm going to stop here because I'm at 14 minutes, and I want you to make sure and read that 2.3 and 2.4. Just browse through it, read through it, and listen to this little lecture or discussion. I don't know what you call it. But I definitely want you to try to do example problem in 2.4, Q1. Example Q1 on page 72. Page 72. I want you to read through that and try to do that problem and see if you can understand the basics there. I'll tell you what, try Q2 as well. Q1 and Q2. Example Q1 on 72 and Q2. Those two. Okay? I will have your problems for you in class that you are to do. And that is it. I'm going to stop recording.